Hello and welcome to the Open Systems Media webcast titled Solving DAL-A's Safety Certification Challenges for Military Avionics Systems. My name is John McHale, Group Editorial Director with Military Embedded Systems and moderator for today's event. Our speakers today are Antoine, Colin, Head of Products and Services with Rapita Systems Limited, Todd Stempel, Chief Technologist and Certification Manager with ENSCO Avionics, and Neeraja Vemulapalli, Vice President, Professional Services and Customer Success with Lynx Software Technologies. Today's webcast is sponsored by ENSCO Avionics, Lynx Software Technologies, and Rapita Systems. Now, before we begin, I have some housekeeping items to go over. This and all Open Systems Media webcasts are copyrighted and may not be recorded or used in any way without the express written consent of Open Systems Media. The webcast will consume about 45 minutes. Leave the remaining time for the question and answer session. Regarding your viewing console, it has some important features that I want to run through. The console consists of a set of windows that allow you to close, open, move, resize, and maximize to your personal preference. On entry, you can see a picture of our presenter in the presenter window and also in the video window, a biography in the speaker bio window, the presentation slides in the slides window, and a Q&A window that enables you to ask questions during the event. There are also a set of 7 icons across the bottom of your screen. Clicking the icon on the far left will reset your viewing area to the default configuration. The rest of the icons will open or close their corresponding window. You can hover your mouse over each icon to show which window it controls. The handout icon third from the right opens the handout window, which has the presenter slides in a PDF format that allow you to follow along or download for future reference. The Q&A window will enable you to participate in today's event. Simply type a question into the Ask a Question text box and hit Submit. Intended for a specific speaker, please note so at the beginning of your question, otherwise I'll hand them out the questions equally to all of our speakers. If you have a question pertaining to the webcast operation itself, one of our technicians will get back to you during the webcast. We encourage you to ask as many questions throughout the event while the question is still fresh in your mind, and we'll address as many as we can during the closing Q&A session. Please note that as much as we'd like to, we may not get to all of your questions today. In that case, someone may get back to you after the webcast with more information. This webcast will be archived online today at the URL shown on your screen and be available within 24 to 48 hours. Once up, it'll be available for 1 year. So let's get started. I'm pleased to turn it over to Neeraja. Neeraja, take it away.
Hello, everyone. I will be representing Lynx today, talking about the DAL-A safety certification challenges for military avionics systems. And let's start off with some of the very basics. Right. So what is DO 178, right? It's a de facto standard, as you all know, for building safety critical software for aircraft systems. And the DAL, that's the design assurance level, is basically determined from the safety assessment process and the hazard analysis by examining the failure conditions. There are actually 5 DALs, that's DAL-A through DAL-E, the DAL-A being the catastrophic, and DAL-B is hazardous, C major, D is minor, and the E is no effect. And based on the level, it's the number of objectives that needs to be satisfied. And as you can see, DAL-A that we are talking about, or we will be covering today, has about 71 objectives that needs to be satisfied. And what are the DAL-A certification challenges? Actually, this is more broader than DAL-A, right? So we all understand, those who of us in the certification world, in an ideal perfect world, all the planning documents, the system level requirements, the high level, low level, all of it would be in place before you start writing code. But in reality, most of the code exists, and a lot of times, I would say about 70 or 80% of the time, a significant portion of the documentation is reverse engineered from the existing code, right? And what is the biggest challenge that we see? So it's typically done by people or individuals that are not the original developers. And a lot of these issues are found that needs to be addressed. There's a lot of that back and forth that needs to be addressed by the original developers. And this adds significant cost to the software development lifecycle, the risk, and the cost of it as well, as we all know. So this is something unavoidable for the most part, but there are ways you can mitigate how you can have the safety process in place in mind as we are developing new code. But there are always trade-offs, right? As we start developing, right? So there are, if you need to follow all the process, the time to delivery will be not as expected if we need to. So it's always a trade-off that we need to keep in mind as we follow these safety processes. And one of the biggest challenge with DAL-A, as most of us know, is achieving the MCDC coverage. And that is what is unique for the DAL-A, where you need to really show each condition in a decision is independently affects the decision. So that is typically, I would say, the long pole towards the end of the certification as we are trying to achieve this MCDC coverage. And what are the modern challenges, like the actual basic issue with the DAL-A, right? So as we said, the DAL-A objectives, they really do not talk about or address the multicore determinism issues, right? So the CAS32A is one thing which introduces the multicore processor determinism concerns and ways to mitigate, mainly covering the robust partitioning, the worst case execution time, and the interference channel analysis. And most of the interference channel analysis that we're talking about, there is a TC1651, which I'll be talking about a bit here, which it talks about the source of the MCP, the multi-core processor issues, and the mitigation techniques. And I'll just talk a bit about it in the next slide, which basically introduces top-down, bottom-up approach in handling this interference-aware safety process, right? So the main thing that it shows is robust partitioning is conditional based on usage domains as well. And I'll talk a bit about it in the next slide. So as you can see with the next slide, so the concept is basically, it's pretty simple, right? So as we can see, it preps for the determinism of basically the concept of there's a platform usage here, which is mainly the scheduling and the security policies here. And then there's a processor usage domain, which is the resource allocation part of it. And it's typically basically preps for the determinism of the mitigation strategies here for the sources of non-determinism that remains in the usage group, as we can see. And there are 3 steps, right? So what it really does is identification of the interference, and then there is the analysis and the mitigation techniques that are applied here. So how is Lynx solving this problem, right? So that's the part that I will be getting into as to how Lynx is going to address. As we can see, the Mosaic, the product that we have, is a modular open system, right? So it's a cross-development platform for building and integrating, it's basically, as you can see, there is an RTOS, an embedded Linux, and the bare metal apps. And, there's a inter-process communication as well between this, right? So the key thing that we are talking about here is this is basically clearer path to the multi-core certification, because the processor, the resources are partitioned based off the architectural, the configuration policy. And the policy we are talking about here is a least privileged control plane. Basically, that is what makes it unique and simple and helps with the multi-core certification as well. And I'll talk a bit about the Lynx 178, one of our products as well. The functional capabilities are basically, it's a hard real-time OS, and it's ARINC 653 time and space partitioning as well, compliant with that. And as it's a POSIX specification, as you can see, and it's a phase compatible as well. And it's the first FAA certified reusable software component, which is the first OS that is awarded that. And it has gone through several versions of the 178, has been certified to the DO-178 DAL-A as well. And I'll talk a bit about what RSE is, the reusable software component here, right? So basically, it's you certify once and you can deploy often, right? So these artifacts are portable and reusable, so you really do not need to recertify all of it. And it saves a significant amount of time, basically, as part of the certification review as well. So that's something that is, it's the first OS, as I said, that has been awarded this. So that makes the certification or the recertification process much smoother. So as I said, there are three things that I would like to touch on, right? So how is Lynx Mosaic, the software, handling it? As I said, it's the unique architecture that makes it simple, and you know, the how we simplify the timing complexity and the usage domains, which we touched on before, and the mitigations that I'm talking about here. And you know, also from a robust partitioning standpoint, as we discussed, right? So there is a robust times partitioning and the space partitioning part of it here. With respect to the time partitioning, it's basically the responsiveness of the shared resources in one partition you need to ensure cannot be affected by the software in another partition. Right, so there are few techniques or things that we've implemented. One thing is the cache allocation technology, which we can talk about, which is a configuration parameter, which is the last level cache, which is called LLC. And we can just give a percentage of the LLC that can be assigned to each partition, and that's one way we can mitigate. And then there is a cache monitoring technology, and there is also a memory bandwidth monitoring that that's been in place, and we can call these as a few of the mitigation technologies or the implementations that we have that will help with few of these. And on a partnership level, we are working closely with Rapita on the timing analysis part of it, doing the integration with their tools, so that can help with the Multicore timing analysis as well. So that's an ongoing project for the last year and a half, or maybe a little more than a year. So that's a work in progress. So that's pretty much all I have. Back to you, John.
Thank you, Neeraja. Excellent presentation. Just want to say to the audience, if you have any questions to Neeraja, please send them in now while they're fresh in your mind, and then we can get to them during the closing Q&A session. Right now, I'm going to turn it over to our next speaker, Antoine. Antoine, take it away.
Hi. My name is Antoine Colin from Rapita Systems. And if you've not heard of Rapita Systems before, I've got a quick introduction to who we are, where we started. So we started in 2004. We are a UK company. And when we all started this company, we started with a tool solely for providing a solution for time analysis, WCT in particular, for the needs of DO-178. Since then, we've extended our offering. We are mainly tool providers. We've extended our offering to cover structural code coverage analysis, various type of software testing, scheduling analysis, and a lot more. And our latest venture took us right back to where we started, as we've now been tackling for a couple of years the challenge of performing time analysis on multicore systems, which is one of the recent challenges that everybody seems to be encountering in the industry, both military and civil. I'll talk about that a bit later. So first, let's go back to the question of DO-178 in the military aerospace. So, as Neeraja explained, DO-178 has been the basis for anything to do with approval of any commercial aerospace software system for a long time now. Even though that's been used for decades in the civil market, the use of DO-178 processes for military projects is relatively recent. When you say it's not a few years old, but no, it's been used more and more recently. So why only recently? Well, for decades, military organizations have been using their own hardware, software, and specialized standards to go with it. And one of the reasons why that was the case is because military applications were perceived as different. Their main concern often was mission rather than safety. So that's one of the big difference. Some other perceived difference, at least, were that systems were more complex than commercial, which in part is true. There's a more varied set of systems that needs to be integrated in military aerospace. That they needed higher reliability in harsh environments. That was another difference, and that the type of suppliers that they were managing were much different as well. So, despite all this perceived difference, there has been a move towards converging these two avionics domain, military and commercial, towards adopting the same processes, in particular DO-178. And there's been already many examples of military programs which require compliance to DO-178. I've got some example from the C-130 cargo planes of the A400M in Europe and some of the UAVs that we've seen recently. So why now? So, well, one factor is that military aircraft would very much like to operate as much as possible in civil airspace with more freedom. And that does require to comply with DO-178 in a big part. Another aspect is that as the industry moves towards using more off-the-shelf components, it makes more and more sense to reconcile the differences between military standards and commercial standards so that everybody can benefit from the same suppliers. So this brings a lot of benefits, such as a lot of cost reduction potentially, better interoperability and reuse of hardware and software. And I think these are some of the reasons why DO-178 is now the worldwide de facto standard for military avionics as we speak. So some of the benefits of following the DO-178C process, well, one can point to the improvement in collaboration and transparency, meaning that every actor in the supply chain can standardize on one approach for certification, which means that it's easier to reuse subsystems, easier to use COTS. Greater assurance is also something that, as Neeraja explained, is something that comes with the DO-178 process, where very early in the design, the design assurance level is determined from the safety assessment process and the hazard analysis. So this means that for each piece of software module, or each module of the software, it will be verified to the right level of rigor. The requirement first approach of DO-178 means that everything can be traced very easily from high to low level to the verification artifact. Everything is then tested and analyzed as prescribed by the DO-178 guidance, and it makes for a very consistent approach to software verification. Everybody's doing it the same way. It's easy for the certification authority to really do their work as well. Finally, one other aspect is system reusability. Again, something that Neeraja mentioned is that following DO-178's guidance, does lead to an increase, at least potential, for reusability of the software component. So it's something which is obviously very, very important to commercial aerospace, where we provide version after version of a variant of aircraft. It used to be less so in the military, but it's becoming more and more important as well. So one of the challenges of applying DA-178 to military projects, as I think it is the fact that military projects tend to be, let's say, more advanced in their use of the technology. So the technology used in military systems tends to be more varied and sometimes more cutting edge than most commercial programs. This is driven by the need, a very, very wide need and requirements from military systems. So some of the examples where, let's say, military aerospace has adopted technology earlier than civil. The use of GPU, for example, GPU for either graphics, think smart helmet, for example, or other application like image processing or radar processing. So GPUs is not something that we use in civil beyond let's say rendering graphics very often. On the military side, this step has already been taken of moving on to a general purpose GPU for various applications. Multicore is something which is coming to civil, which has been used already in military avionics because of the benefit it brings. In terms of reduction of size, reduction of weight, reduction of power, reusing common off-the-shelf processing platform. The power coming from Multicore has been very, very important for more recent military projects. And things more advanced even, like AI for autonomous operation of UAVs, for example. That's something which is very, very far away for civil, but military is already considering it. So these are topics where, let's say, the civil aerospace had, until very recently, very little experience to offer. And where, let's say, there are still some gaps in what DA-178 guidance can provide there. So this is going to be one challenge where, by adopting DA-178 with a more advanced set of technologies, maybe we're going to have to get, to catch up for providing guidance on how to use this under DA-178. So, as I mentioned earlier, one area where Rapita Systems has been very, very active in the last few years has been Multicore. And or multi-core, depending on how you pronounce it. I'll pronounce it the French way, so multi-core. So yeah, Rapita has been developing an approach to address the use of multi-core for certification, as described in the CAS32A paper. So there is an upcoming, I don't know if it's out already, AC or AMC 2193, which is going to supersede CAS32A. They are broadly the same, and our approach applies to both of them. And it's an approach which relies on our experience of providing tools for the market. So we've got a tool offering called Rapita Verification Suite, RVS, which provide testing and timing analysis capabilities. And we also have recently worked with what we call multi-core interference generators that we call RapidDemons. So combination of these two allows us to provide a solution to how to go about certifying your multicore system in terms of timing analysis. So we do also offer multicore timing analysis services using solution to support your certification. As part of this work, we are not just working on our tool and our approach, we're also participating in the effort to produce new guidance on this topic. So, for example, we have the Safety Critical System Club, which has got a working group on multi and many core safety. We're also taking part with some of the partners like Lynx in research activities. So we've been recently working on a project called Mastex with Lynx and Raytheon and other partners. So this approach that we've devised, I'll give you a bit more information about it. So very, very quick overview of how we tackle this challenge of multi-core timing verification. Well, we're using some of our tools, as I said, so mainly RapidTest, which is a test driving tool, and RapidTime, which is our original timing analysis tool. And they are all used in conjunction with the rapid daemons, which are there to generate interference on your Multicore platform, and they automate as much as possible of the testing. So the tests are designed to exercise various aspects of a Multicore system. For example, to quantify maximum impact a particular interference channel can have on an application software. So as Neeraja said, think shared cache, shared buses, shared resources, anything which is shared between two cores could be used as an interference channel for one task on one core to impact another one on another one. So, well, as a simple example, you can imagine two tasks on two cores trying to access the same main bus at the same time. The question is then, what is the worst level of delay or interference that one task can cause on the other? Another goal of multi-core time analysis can be to verify that all the mitigation techniques that we put in place. So, for example, Lynx comes with lots of mitigation techniques to make sure that the interferences are kept in check. Well, despite having all these things in place, you do need to check that they are effective, that they have been configured correctly, that they are effective for your particular platform. So when we do that, we run all these tests with these interference generators, and we collect lots of metrics. It's not just about the time it takes to execute a piece of code. There's a lot more timing metrics available on the platforms, on modern platforms, so we can count things like cache misses, a lot of various metrics that can be used to establish that yes or no, this interference channel has been mitigated properly, for example. So I think one of the important factors of our solution is the automation. In my opinion, automation, a very, very high level of automation, is crucial to be able to achieve certification of a multi-core system. So by automating as much as possible, we make it possible to tackle verification problem, which is much more complex than anything that we've been used to in single core systems. The number of combinations to consider when performing multi-core analysis means that a manual approach is just not economically feasible. There's just too many variations on a multi-core system that needs to be considered. So as an example of a project which is currently running, we've been very fortunate that for Bellfly to choose our approach to tackle their needs of certification for one of their systems, part of the future attack reconnaissance aircraft. I can't say much about it. One thing I can say is that everything's going fine so far. And one of the interesting part of this project is it's part of their wider goal of being phase conformant. So phase, obviously, very, very important aspect of in the military world. Phase, for people who not looked into that yet, it's a government and industry partnership. It's the future airborne capability environment. So it's trying to define and succeeding in defining an open avionics environment for all military airborne platform types. So the focus of phase is to be complementary to DO-178. So DO-178 goes very much into the detail of how things should be done and give guidance on very practical aspect of it. phase is more about the standards and making sure that things are going to work together. So interoperability, standardization, making sure that we can reuse things. So phase certification indicate adherence to the phase technical standards for portability purpose mainly, whereas DO-178 certification governs the processes for software development and verification, and it's a far more rigorous certification process. We are, Rapita Systems, we are involved with phase in two components. First, the tooling. So we make sure that our tools can provide capabilities to test and optimize phase conformant software, for example. There are things like being phase compatible with the operating system. So if you do that, then it makes it very, very easy for us to integrate our tooling with operating systems, which are phase conformant. And the other aspect is related to CAS 32A. So one of the things that phase does mandate as part of this is what they call profiles, is most of the profiles must include an ARINC 653 partitioned OS. Now, ARINC 653 does provide robust partitioning, but it doesn't assure it. So it's one of the interesting things, as it does provide it, but the assurance is not there. So when you use FACE and the ARINC 653 that comes with it, the conformance to the FACE standards implies that you have this partitioning, but it doesn't imply that it's actually robust. It's not assured. So that's where CAS32A, D178 and therefore CAS32A come in place. That that's the part that is going to allow you to verify the robustness of the partitioning. Another area where we've been quite active in one of these more advanced, let's say, usage of technology is the use of GPU for both military and now civil avionics. So traditionally, GPU has been used for display systems. That's their natural place for use. More recently, we've been looking, or people have been looking at using the power of GPUs for general purpose computing. Anything that's highly parallelizable, GPU is ideal for that. And after discussing this with some of our partners, in particular Core AVI, we realized that one of the limiting factors for people using more GPUs in their system is that there was a lack of support for certification. That is something where the guidance doesn't yet offer a lot of information on how to do it. The tools are missing as well. In a lot of cases, there's a lack of tooling. It's not like GPU doesn't come with tools, but they are not always adapted for the purpose of producing software for certification. So it means that a lot of time verification requires more manual work than on CPU-based software, just because the tools which are available are not necessarily appropriate. Tools are typically used for CPU-based software. Is typically written in C, C++, or Ada. GPUs are not programmed in these languages. So yes, there is a lack of tool, and therefore the burden of having to do a lot of the D178 without the help of tool to streamline the work has been a limiting factor. Another aspect of the challenge of using GPU is that a lot of the guidance and concept which have been developed during for D178 don't necessarily apply directly to GPU. So yeah, there are things that just are very difficult to translate or need some thinking before translating them onto GPUs. So I'll give one quick example of interesting example that we encountered recently, where we've been looking at providing code coverage, structural code coverage. We've got a tool called Rapita that provides structural code coverage for up to DAL-A, so it does MCDC for CPU code. So one of the things that we realized quite early on is that code running on CPU and code running on GPU, although it may look the same from afar, it doesn't actually execute the same. So as a very quick example, you can see that some generation of GPU, so also that's something which is different between CPU and GPU, is there's lots of variety between how GPU are being implemented. Some generation of GPU implements condition using predication or condition codes, as they're sometimes called. So it means that an if-then statement compiled to one of these GPU architecture is actually going to evaluate both the taken and the not taken branch for every set of instruction of all the fragments of the code which are being executed in parallel. So you can see that on the CPU side, we can clearly tell from the first condition A equal 1 being false that the second one is not being executed. On GPU, not so. The branch condition is going to be evaluated. Condition code is going to be set. The instruction that should not be executed are going to be executed anyway. But then the part of a branch that should not be executed is going to check the value of the condition code before writing results registers. So it's something which does work very, very well for massive parallelism, where everything executes exactly the same instruction all at the same time. Well, one of the issues is then, what does it mean to execute an instruction anymore? So something as simple as statement coverage needs to be redefined for GPU for such a mode of execution. So unlike on a CPU, where what matters is just checking whether the statement is executed or not. Now we're faced with the extra work of figuring out, okay, well, the statement is going to be executed. Has it been executed with the right value of the condition code to see if this thing is actually being tested as part of the test? So we've done some research that would allow us to extend our SCA tooling to cope with this kind of differences. And we've been looking at other things like, what does it mean to do unit test for GPU, for example? So these are some of the challenges that are just coming online with, let's say, military projects using DA-178. As a conclusion, I would say that DA-178C is indeed becomes the de facto standard for both civil and military avionics for quite a few years now. It is important to note that military systems do bring their own set of challenges to the DA-178C certification process. And there is no doubt that they will accelerate the development of the guidance for the use of, let's say, more advanced technologies like GPUs and multicore, and how to certify them. But with close collaboration of the industry, our partners here, everybody is working together to try to address these things. I think the industry will take these challenges on and will overcome them. We will be able to define the best practices and best ways to address these new technologies and challenges. Yeah, that's all I had to say today. So, John, back to you.
Thanks, Antoine. Excellent presentation. And just a note to our audience, if you have a question for Antoine or for Neeraja before him, please send them in now while they're fresh in your mind. We'll get to them when our closing Q&A session starts, which will be right after our next speaker, whose name happens to be Todd. Todd, take it away.
Okay, thank you, John. Great details from Neeraja and Antoine. Thank you very much. So in thinking about the best way to expose the largest issues facing DAL-A compliance in military air vehicles, I think projecting a picture of the environment and capabilities that we can expect in the future is the best way. For DAL-A compliance, it's easier to know how to do it after it's been done. And we've all heard the expression that hindsight is 20/20. And to that, I'll add, it's difficult to know what you don't know. So I'll be asking you to envision what the airspace might look like in the future, thinking about which major technical and process factors were probably central to realizing that vision. Think about what the world was like 25 years ago, and think about the accelerating rate of technological advancements currently, and then ask ourselves, what will we be looking at in the national airspace and this highly connected battle space 25 years into the future? Finally, we'll consider some steps that should be taken now to best realize that vision. So I think what we need to expect is a very physically congested and highly interconnected airspace with a broad range of vehicle types and missions. The path to DAL-A certification will be supported by development and verification environments that take advantage of digital transformation and digital twins to accelerate the software lifecycle and certification processes. There will likely be greater synergy between civil and military airworthiness standards, as we've already envisioned a confluence between the airworthiness objectives. In any case, what kinds of advanced capabilities should we expect from the vehicles operating in this environment? Well, we should assume advanced positioning systems with predictive and prognostic capabilities that augment pilot control to automatically avoid air and ground collisions while simultaneously reducing pilot and crew workload. Cloud-based software maintenance will probably be a reality for most of the vehicles in this airspace, civil, industrial, and military, which means that these vehicles will have cyber-hardened systems that are resilient to enemy cyber threats. Expect manned, unmanned, and optionally manned vehicles to share this airspace with artificial intelligence playing a significant role. Though it's not entirely clear whether we'll have truly autonomous systems making independent decisions, it's clear that we'll have increasingly autonomous systems in operation. Computing power and network interconnectivity between ground and air and between air vehicles will be significantly greater than it is today. And we have to assume that military and civil air traffic management systems will coexist and be harmonized with unmanned traffic management systems that supports industrial unmanned UAS and package delivery and potentially air taxis. So you have to ask, what technical and certification solutions must we have figured out in order to realize this kind of a future airspace? It's easy to suggest that we'll have secured solutions for many of the DO-178C challenges that we face today. And it's reasonable because having the advanced capabilities is probably only feasible if we can use every available technology, including certification disruptive technologies that constrain DAL-A compliance. Among the technical advancements that I think we'll see, I believe there will be three significant process achievements in achieving that vision. We'll have compiled a deep catalog of modular, interchangeable, certifiable software components that will serve as the basis of compliance, where certification data is accrued along with the components as a natural part of their acquisition. Platform integrators will achieve operational flexibility, accelerated integration, and more rapid deployment based on the availability of software packages that are positioned for DAL-A compliance. Second, I think we'll employ airworthiness methodologies and frameworks that support continuous certification, a structured, iterative framework that will ensure timely periodic evaluations and assessments to detect and avoid certification compliance risks before they are allowed to persist and become part of technical solutions that may be too expensive or too risky to address or remove. And lastly, a digital transformation that harnesses the capability of digital twins to accelerate development and verification processes and allow developers to fully vet solutions in simulation prior to target testing. But what are the most significant disruptive technologies that need solutioning now? So before we talk about that, I'd like to throw some attention back to the software development environment in the 1990s. For those of you that are around, we were seeing modeling tools being developed and applied. Avionics software developers started using graphical signal and control flow integrated development environments that could also generate code. Modeling tools offer palettes of functionality, meaning functional components or building blocks that could be applied over and over, where code could be reliably generated from applying those building blocks in different combinations. Initially, model-based development tools were considered significant DAL-A disruptive technology, but today model-based development and verification is almost commonplace. In addition, the FAA has recognized the guidance of DO-331, Model-Based Development and Verification Supplement to DO-178C and DO-278A, as an acceptable means of compliance to airworthiness regulations. Now, the message to take away is that novel technologies tend to have disruptive effects on DAL-A compliance initially, until the use of those technologies has matured with the development community, regulators, and airworthiness organizations. So, like I mentioned, disruptive technologies impact determinism and have often insufficient initial guidance, but they're often critical transformative technologies in terms of the capabilities that the future demands in addition. So what are the near-term disruptive technologies that are problematic for DAL-A, where solutions are most critical to this future airspace? So as we've heard, Multicore offers significant swap-C benefits and are probably the largest disruptive technology that we face today. FAA Advisory Circular 20-193 will likely be published by the FAA later this year as an acceptable means of compliance. But honestly, little progress has been made in successfully certifying safety-critical systems that employ Multicore to date. So it's clear there's significant need for multi-core interference analysis tools and multi-core specific domain knowledge that can satisfy DAL-A objectives. So achieving certification with COTS software, open source software, or COTS IP for complex electronic hardware has challenged designers of systems that need DAL-A compliance for many years. Some third-party COTS suppliers provide certification data, but some suppliers don't provide any data at all, and it's not typical to have sufficient data when employing open source software. This can lead to the need for reverse engineering of requirements, design, and other lifecycle data, which is a significant risk to cost and slows development and deployment. RTCA Special Committee 240 is expected to provide guidance for DAL-A compliance for COTS and open source software by the end of the year. And that may be guidance that's accepted by the FAA for COTS and open source software. So certified UAS flying in the national airspace is being developed currently for lower risk UAS by RTCA Special Committee 240, but now for higher risk operations like urban air mobility, DO-178C compliance is required. Artificial intelligence and machine learning being introduced into DAL-A systems should be expected to be further off in the future probably than most people think. It's not clear how long it will take to have AI control and command capabilities in DAL-A systems, but it may be more reasonable to expect that applying AI and machine learning to software assurance strategies is the right approach as a first step to integrating AI into our environments. So non-deterministic software is a fundamental non-compliance issue for DAL-A software. The software for DAL-A must be shown to perform its intended function and as specified under all foreseeable conditions. Introducing non-deterministic software into safety-critical avionics can offer desirable advantages, but also undermines DAL-A objectives. In the future, we will likely have figured out how to ensure deterministic behavior even in the presence of disruptive technologies like these, or will alternatively have defined new airworthiness certification strategies that will ensure that certain dynamic behaviors, for example, are acceptable. We may have entirely new objectives that address system architectures that mitigate the risks posed by non-deterministic software. So what are some of the paradigm shifts that are in process and required in order to achieve this vision of the future airspace? So first, for development, we need to embrace the consumer software industry and agile processes. And although they may appear to conflict with the highly structured and interrelated software development ecosystem of DO-178C, there's no real inherent conflict. Eventually, agile processes will find a place in DAL-A systems. DAL-A industry stakeholders have to find ways to harmonize continuous development concepts like continuous development, integration, and DevOps within DO-178C programs. Continuous certification is a concept that is expected to change the way airworthiness assessment is performed. DAL-A compliance evidence needs to be accrued continuously throughout software development life cycles to avoid the need to compile those DAL-A objective evidence after software is fully developed and delivered. Finally, product assurance versus design assurance approach. This is a big paradigm shift that's really critical to understand. DAL-A software requires design assurance in order to comply with DO-178C as the proposed certification basis and means of compliance. Product assurance is associated with testing the completed software as built as the basis for establishing that the software performs as intended. Civil authorities consider DAL-A software sufficiently complex to suggest that testing alone is not sufficient to ensure that the design is error-free and therefore require a design assurance strategy. Design assurance approaches impose criteria on the processes used to develop the software lifecycle data, in addition to requiring comprehensive testing as evidence of safety and that the software performs as intended and specified. So, what are the most important solutions that we need to consider? So first, software component modular approach. Monolithic, tightly coupled software architectures are costly to maintain, and they're often difficult to port, scale, or reuse. Using a modular software component approach, software is developed using compartmentalization principles. Each component of the software is developed to implement specified and bounded functionality in accordance with a well-documented interface. This approach advocates and supports interchangeability, portability, and scalability, and leads to future opportunities to realize a catalog of standalone, trusted software components that can be reconfigured and recertified seamlessly for new platforms and mission objectives. So secondly, continuous certification framework. A continuous airworthiness certification strategy is really needed to address architectures, technologies, and development techniques that ensure airworthiness objectives are satisfied in airborne systems in anticipation of any new disruptive technology that suppliers may utilize in their architectures. The continuous certification solution needs to provide surgical guidance for performing evaluation and assessment of compliance evidence continuously throughout the development life cycles. And it's critical for this framework to be developed to anticipate disruptive effects of emerging novel technologies that may emerge in the future, where technology advancements are expected to grow exponentially in complexity and rate. Finally, digitization and model-based standards are a key enabler of this future. New and standardized requirement specification standards are needed to embrace digital transformation of system and software development environments, including model-based systems engineering, treatment of mission requirements to produce system requirements, and model-based development and verification of software. All software functionality and features need to be well represented in requirements in order to satisfy DAL-A verification objectives and ensure that software performs as intended under all foreseeable conditions without anomalous behavior. So finally, ENSCO Avionics provides safety-critical software and hardware services and HMI products ranging from gap analysis and process efficiency analysis to full hardware and software lifecycle support. iData is a data-driven human-machine interface tool suite based on open architecture, and it's well-positioned for MOSA applications. iData is DAL-A certifiable for displays and aligned with industry standards, including ARINC 661 and FACE. IGL can be used to complement iData for software rendering without the need for a GPU. ENSCO Avionics also provides multi-core guidance in conjunction with Rapita's tools and solutions that offer simplified guidance for satisfying Advisory Circular 2193 criteria, and an airworthiness framework that standardizes the criteria sourced from the existing broad set of airworthiness criteria and provides incremental accrual of compliance evidence. So that's all I have. Thanks for your time. Back to you, John.
Thank you very much. Excellent presentation to all three of you. Really appreciate it. Now let's get started with that audience Q&A. My first question is for Antoine. 80 to 90% reuse. What stops it being 100% reusable? Antoine, I think you might be on mute.
I was on mute indeed. Yes, I was saying that we should be looking at the people who have been the most successful, let's say, at achieving this reusability and defining what the AC 20148 defined back in 2004, if I remember correctly, as a reusable software component. So obviously, when you think things which can be reused from one project to the next, we all reuse software all the time, but things which can be formally reused, operating system is the first thing that comes to mind. They are doing that very well. Lynx comes with its own RSC package, so they're doing a good job of that. I don't know how much of it is reusable. There's two aspects which are always going to limit reusability and the amount of work you've got to do to go through certification. Is first, you can't certify something independently from its application at the moment. It's not something that's very, very practical to do. And the other one is how do you account for the interaction between the software and the hardware if you don't have a reusable component that encapsulates both of them. So why not 100%? I think it's really what we should be aiming for, but it's 100% reuse of exactly the same thing. And as we know, every time we want to reuse something, we'd like to change things a bit, which throws spanners in the work, I think. But I think the RTOS people are the people to look at in that domain. They've been doing it very, very successfully. We should learn from how they've done it to be able to reuse other things like software libraries, communication protocols. There are many, many other things that could be reused a lot more.
Thanks, Antoine. Next question I have is for Todd. Was your airworthiness framework aligned with MIL Handbook 516C?
So yeah, the airworthiness framework that we've designed is aligned with 516C, but it's actually modeled after commercial civil airworthiness guidance. And the reason is to ensure the continuous monitoring of criteria throughout the development lifecycle.
Okay. Question for, this one's for everybody, but I'm going to turn it to Neeraja first. What's the biggest technical challenge in certifying UAS platforms today? Is it more of one just getting the government bodies to agree on a set of rules and requirements? Neeraja, you might be on mute.
Oh.
You're off. Go ahead.
Yeah. So the biggest challenge that I see right now is agreeing to basically a set of rules and requirements and the process around basically figuring out what it really translates to on the requirements front that really, maybe I should let Antoine and others take it actually, so.
Antoine, she served you up.
Well, one aspect I know is being a problem for a lot of people is a type of systems which are usually part of this US are quite advanced, and it's not always clear how you go about testing them, for example. Now, one of the things is the type of testing and the requirement-based testing that we do for our Avionics software, the flight control, flight management system, doesn't always translate very well to things which are more complex, which are way more data-driven. So I'm thinking anything where there is a little bit of autonomy, you are very, very quickly moving into what Todd was saying, so things which will take decades maybe to get completely under control, like machine learning, AI, this type of technologies which we can use already very efficiently, but we still don't know how to verify very well. So I think that's one of the challenges. How do you even test these things?
So if I may offer a complimentary comment. The biggest challenge, I think, for the UAS industry stakeholders is that they use a more commercial software development paradigm than is typically expected for more rigid DO-178 development. So they use a lot more COTS, they use a lot more open source software, and they construct their software in an agile context. So it's traditionally been viewed as a bit of a roadblock for DO-178 compliance. And that's why I said we will find ways to harmonize those continuous principles. But that's one of the big roadblocks that's trying to be addressed today by some of the ongoing regulatory work. Thank you.
Excellent. I got a question here from the audience. Is there any safety certification for a lockstep redundancy system? This is not assigned, so whoever would like to take it.
I can go in. DAL-A requires. Sorry?
I thought Neeraja was about to answer. I'm sorry. Go ahead.
No. Go ahead.
DAL-A requires safety certification regardless of whether you use a multi-core in lockstep. The difference is that CAS 32A and AC 2193 does not require compliance when your multi-core is in lockstep mode.
Yes, it's not considered a multi-core system if it's lockstep.
That is correct.
Products. Why do we need to verify multi-core timing? Antoine?
Okay, so yes, why? So if people like at Lynx are working so hard to put a mitigation system in place, why don't you trust them? Well, it's a principle. One of the principles of D178, you have to demonstrate it. No, you can't trust as much as you want, and we do trust that we've done as best as we can. You do have to demonstrate it. It's as simple as that. You can't just claim until there is something that says that Lynx OS on any platform you put it, the mitigation is definitely going to work. You do need to present some proof that you've done your due diligence and check that it is working. So there's no. It's always better to have to show that something is working as it should than not knowing what you're supposed to be demonstrating in the first place. So you are already starting from a better position, but you have to do the work anyway.
You got to make it work. Last question, and this one is for Todd. Todd, is ENSCO multi-core process shown to comply with CAS 32A?
So we developed our guidance in accordance with CAS 32A, but we're currently in the process of upgrading that guidance to align with Advisory Circular 2193, which is expected to be the accepted means of compliance for multicore. There's not very much difference between CAS 32A and AC 2193, but there are some subtle differences. And for that effort, we're actually partnered with Rapita using their RVS suite as the method for mitigating the risks of interference.
Excellent. Well, that brings us right to our time limit for today. Sorry we cannot get to all of your questions. Someone may get back to you after the webcast with more information. I want to thank Antoine, Todd, and Neeraja for speaking today, and ENSCO Avionics, Lynx Software Technologies, and Rapita Systems for sponsoring the event. This and all Open Systems Media webcasts are copyrighted. It may not be recorded or used in any way without the express written consent of Open Systems Media. This webcast will be archived online today and be available for 1 year. There'll also be an MP3 version of the event available. Thank you all for attending. I look forward to seeing you in future Open Systems Media webcasts. Goodbye.